What questions do you have?
Oh, light up attendance.
You tripping? They should have been here.
What's that?
That's what they should have been.
They should. That's right.
It's like
Feels like slacking, doesn't it? Oh, goodness. All right. So I can get rid of that thing. Or maybe not. That's fine. All right. We talked last time about row space, column space, null space. What was the definition for the row space again?
The span of the row.
Good. Exactly right. It's a set of all linear combinations of the row vectors. The span of the row vectors. Exactly right. Column space.
Span of the column.
Span of the column vectors. Good. A set of all the linear combinations of the columns. How about the null space?
This is the solution to the homogeneous.
Good. Yeah. So it's the solution space of your homogeneous system, right? So we did all three of those last time.
Pardon me. We also talked about rank. What was rank again?
The number of pivots and reduced row echelon form.
Yeah. So rank is your number of pivots that you get when you row reduce your matrix, right? It gives you the dimension of what?
The column.
The column space and the row space, right? So remember that we talked about how we find the basis for the column space, basis for the row space. For your basis for your row space, you row reduce, and you take the actual rows that you get when you row reduce, right? That gives you your basis for your row space. Again, we talked about that you have to use especially if you're using technology, you have to use the row vectors that you get when you row reduce because you don't know if you've done these swaps or not, right? So the rows that you get in your reduced row echelon form don't necessarily match up with the rows that you started with, right? They could be flipped, okay? That's why you have to use the rows in the reduced row echelon form. However, for column space, how do we find a basis for the column space?
you reduce row echelon form, then go back to your.
Good. Right. You do your reduced row echelon form, look for the columns with the pivots, and then go back and match them up with the columns from the original. Right? Okay. So be careful when you look for those bases for those two different spaces. For your null space, we do it just like we have always done all semester with finding your solutions, right? The dimension of your null space, you look for those free variables and write everything in terms of those free variables, right?
What did we call the dimension of the null space? What name did we give that for the matrix? Nullity. Yeah, that's the name for that one. Okay, cool. All right. So what I want to talk about today is some of the relationships between
The dimensions of these spaces, the rank, and the nullity. So just
write down again the rank of the matrix is the same as the dimension of the row space of the matrix, which is the same as the dimension of the column space of the matrix, which again is the number of pivots in the reduced row echelon form, right, of the matrix. Okay. Did all that last time, all right? And then the nullity is the dimension of your null space, which again is the number of columns of A that don't have a pivot, or the number of columns of the reduced row echelon form of A that don't have a pivot.
number of free variables. All right. So let's see how these things change as we look at, well, I guess that was my dimension of spaces piece there. Let's see how things change when you do the transpose, right? Well, notice that we said over here that, can't get to it easily. We said over here that the rank
is the dimension of the row space and the dimension of the column space, right? Both. Okay? What happens when you take the transpose? What does your transpose do? It swaps the rows and columns, right? So your row space, your row space of A should correspond to what for the transpose? The column space, good. And vice versa, right? Your column space of the original should be the row space of the transpose. But what do we know about the dimension of the row and the column? What do we know about the dimensions for the row and the column space? They're equal to each other, right? And they're both called the rank, right, of A. The dimension of the column space has to be of A has to be the same as the dimension of the row space of A transpose, and vice versa. So what can I say about the rank of A and the rank of A transpose? Well, must be true. They're equal to each other. Good. So these two things that we get here tell us that the rank of a matrix is unchanged when we do the transpose. Okay. Which, if we just think about it in and of itself, is kind of an interesting. I mean, when we think about it this way, it's not too surprising. But if we were just to say rank of A and rank of A transpose were the same, really does say something in terms of what happens when you row reduce, right? Rank is number of pivots that you get when you row reduce. So it doesn't matter if you row reduce A or row reduce A transpose, you'll get the same number of pivots each time. Now you will get a different reduced row echelon form, most likely, okay? Depending on the size of the matrix and how the matrix behaves, but the number of pivots doesn't change, which is kind of a nice little statement. All right. Pardon me. For columns of a matrix, what do I mean by that? Well, look at these two relationships here. I look at those two relationships here. This is, and think about it in terms of columns. This is number of columns with a pivot. This is number of columns without a pivot. Well, as you go across the reduced row echelon form, you're going to get a pivot in a column or you're not. That's going to take up the entire number of columns, right? We agree with that? So this columns of a matrix idea, my goodness, sorry. The columns of a matrix idea is talking about when I take the rank of A and I add the nullity of A. What I'm talking about is I count the number of pivots in the reduced row echelon form, that gives me the rank. I count the number of no pivots, I get the nullity, right? But as I go across columns, either I have a pivot or I don't. So what should this equal when I'm done? If I add them together. Number of columns, exactly. So this will equal the number of columns of A. We refer to this equation as the rank nullity theorem. The important part to remember here is that it's number of columns of A, not necessarily number of rows of A, right? Yes.
So the rank constant number of pivots on the
It doesn't matter when you count pivots, it could be columns or rows. Because if you get a pivot in a column, you have to stair step, right? You have to move. If I move it to a different column, I have to move to a different row to get another pivot. So I can count pivots in columns or rows, they always have to be the same. But for this theorem, I'm looking at free variables, so I have to look at the pivots, the columns without pivots to get the nullity. So that's why I'm just concentrating on the columns. But for the rank, it doesn't matter if you count pivots in columns or pivots in rows, it's the same every time. So then the dimensions of the spaces here, this again is what I'm talking about off to the side. My goodness, I don't know what's making me cough so much. That's what I'm talking about off to the side with the rank again is that, I'll just write it again even though I've written it off to the side of the paper already. The rank is your common dimension of the row and the column space. Which now, of course, since we talked about the transpose, must also be, why did that just stop working? Okay. Which is that common value of the dimension of the row and column space of the transpose. It has to be that common value as well. And then again, your nullity is the dimension of, oops, the null space of A. Now I have to be a little bit careful. I can't write this is the same as the nullity of A transpose. It's not necessarily equal unless it's a square matrix. Let's think about why. If I had, I'm not going to do any row reduction on this at all, but if I had this matrix, at least how many free variables will you get when you row reduce? One, right? I run out of columns, don't I? I'm going to get at least one free variable, right? Without a doubt. But if I do the transpose, am I guaranteed that anymore? No. Okay, I might have, this could have, and it does have, this matrix could have nullity equal to 0. Okay. So I don't get that nice relationship like I have in the previous part, where I've got all of these things have to be equal, whether I'm in the matrix or in the transpose. I don't get that nice relationship for the nullity. Okay? And think about why, again, if you think about the rank nullity theorem, the rank plus the nullity has to equal the number of columns of the matrix. The rank doesn't change when I take the transpose, but the number of columns might. So the equation might change. Okay. So I don't get a nice relationship here necessarily like I did in the previous one. That makes sense? So let's phrase some of these concepts now in terms of consistency, in terms of span, in terms of linear independence. All right. So let's say we start with a matrix A and augment. So basically this is trying to solve the system AX equals B, right? We agree with that? Okay. Now let's think about it in terms of pivots. If this system is going to have a solution, if this system is going to be consistent, well, I'll get pivots this way when I reduce by A. If it's going to be consistent, do you want a pivot in that last column? What does a pivot in that last column mean in terms of the system? Yeah, so let's think about what happens, right? If you get a pivot in that column, say I have a pivot down here at the bottom, what had to be on the left-hand side of that bar? Zeros, right? That's what it means to be a pivot, right? If I get a pivot in that column, that means I get a pivot across that row. If I got a pivot across that row, everything in front of it in that row has to be a 0, right? That makes it inconsistent, right? So what does that mean has to happen for the rank didn't leave myself a lot of room here. The rank of A and the rank of not A transpose. The rank of A augmented with B. If it's going to be consistent, what needs to be true about those two ranks? They better be the same, right? Because again, if they're not the same, what had to have happened? Well, I added an extra column, right? So if the ranks aren't the same, how much more would it be if they're not equal? It had to be one more, right? Because I only added one column, right? I can't get 17 more pivots if I only added one more column, okay? So it had to be one more. And as we agreed that if it's one more, then I had that inconsistent part, right? So if it's going to be consistent, then the ranks will be the same, right? So this is true. Let me erase this part just so I can get back to where I was. This is true if and only if the AX equals B is consistent. Okay. Again, either the ranks are the same or the rank went up by one when you augmented. It's the only possibilities, right? You only added one more column, so the rank can only go up by one more. If it went up by one, that means you had this situation in one of your rows, which means it was inconsistent. So consistent if and only if the rank doesn't change. Okay. All right, let's think about the next one. When you, pardon me, when you were looking to see if a set of vectors span the vector space, what did you do? The row reduced, right? But what did you do first? You put them in the matrix, but how did you put them in the matrix? In columns, right? We put the vectors in the columns of the matrix, row reduced, and then what do we look for? Pivot in every row, right? Agree? Okay. So if I get a pivot in every row, if A is an M by N matrix, and the columns, span, where do the columns live again? RM or RN? Are the columns go this way? RM, right? There's only M components. So if the columns span RM, then you said we had to have a pivot in every row. What does that say the rank of A has to be? Probably greater than or equal to 1. But in particular, what does it say what does it have to equal in this case? It has to equal the M, right? Because there's M rows, right? Remember, span correspond to pivot in every row. There are M rows here, so we have to have a pivot in every single row. Okay? So that means we have to have M pivots, so the rank has to be M. So, well, hopefully it's obvious. The rank of a matrix can be as large as the smaller of those two numbers, right? So if you had a 5 by 7 matrix, the rank could be at most 5, right? Because where your pivots go stair step, right? You can't repeat a row or a column for your pivots, okay? So if I only have 5 rows, I can have at most 5 pivots. If you had an 8 by 3 matrix, you can have at most 3 pivots. So the rank could be at most 3. Does that make sense?
Yeah.
Okay. So again here, this is actually an if and only if, even though I didn't write it this way. Your matrix has a rank M, will tell you that your columns span RM. Okay. Let's go the other way. How did you check for linear independence? Pivot in every column, right? Right?
So if A is an M by N matrix and the columns are linearly independent, oops, then what must be true about the rank? That would be the N, right? Because you have to have a pivot in every column again. Now, one of the examples we wrote down earlier, I wrote that 2 by 3 matrix. And you already told me the rank had to, or excuse me, the nullity had to be at least 1. So would those columns have been possibly linearly independent then? No, there's too many columns, right? If you have more columns than you have rows, the columns can never be linearly independent. And vice versa, if you have more rows than you have columns, the columns can never span. Because you don't get them in the right spots, right? You don't get pivots in the right spots. Now, if you get a pivot in every column, if you get a pivot in every single column, is it possible to get infinitely many solutions if you get a pivot in every single column? Okay, so I suppose it's possible, but it depends on the matrix, right? Or sorry, you get a pivot in every column, you can get infinitely many solutions. I don't know what I was trying to say there. I'll think about it in a minute. Anyway, does this concept make sense what we're talking about though? All right, so let's go to square matrices, and we haven't been back to mega theorem for a while. All right, it's been a while. We got a lot to add today. What was the last letter we used? G? All right. We have a lot to add. We've got statements in terms of rank, we've got statements in terms of nullity, and we've got statements in terms of spanning and all those things. So, all right. Since it's square, we can say a lot of things about row space, column space, and all those things. In particular, again, how did we figure out the rank of a matrix? What did we look for? For rank, what do we look for? Pivots, right? Remember, one of the things that's equivalent to being invertible is that the reduced row echelon form is what? What has to be the reduced row echelon form of the matrix if it's invertible? It's the identity, right? What's the rank of the identity matrix? If it's an n by n, what's the rank? N, because there's a pivot in every column and every row, right? Okay? So another thing that's equivalent to being invertible is that the rank is n. Okay? If the rank is n, what does that do to the nullity? What does it make the nullity? 0, right? It's an n by n. Remember, rank plus nullity equals number of columns. Bless you. Right? Rank plus nullity is number of columns. There's n columns and it has rank n. So there aren't any free variables. Right? So another equivalent statement is the nullity of A is 0. So those are two statements in terms of rank and in terms of nullity. Let's talk about what the row space is. Bless you. Let's talk about what the row space is. Let's think about it in terms of dimension. The row space and the column space. But the row space is a subspace always, because it's a span, right? Spans are always subspaces. It's a subspace of R what? N, right? It's Rn. They're both Rn in this case because it's square. Remember, you go across the columns to get your where the vectors are in Rn, or the row space, I mean. In this case, it's Rn, right? So Rn has dimension. That's your question. Rn has dimension n, right? Okay. What's the dimension of the row space in this case?
also n, right? So can the row space be any bigger? No. It takes up everything, right? So in this case, your row space is all of Rn. So if the rank is n, your row space is all of Rn. Okay? How about your column space? Those are also Rn, good. The dimension of the column space is n, the dimension of Rn is also n, so they must be equal to each other. The subspace must be everything in that case. Yep. It's just the zero vector, good. Remember, we've already showed way back when we were doing systems of linear equations that being invertible is equivalent to the homogeneous system having only the trivial solution, right? Those two were equivalent to each other. Okay. So if the homogeneous system only has the trivial solution, and this is the space that is all the solutions of the homogeneous system, it must be zero. The null space is just the zero vector. Yes.
When you say column is A, it's twisted.
I mean that you can generate everything in Rn using the columns of A. If you do the set of all linear combinations of the columns, which is what the column space is, that gives me every single vector in Rn, but I don't miss anything. That's what that means. All right, so then there's a few here that talk about what we just mentioned. If the rank is n for a square matrix, then I get a pivot in every row. And that tells me that the rows of A span Rn, right? That's how we got span. We agree? Okay. That's also how we got linearly independent, isn't it? So the columns of A are linearly independent. That's how we checked, isn't it? That first statement, M, is just that we have a pivot in every row when we row reduce. The statement N is that we have a pivot in every column when we row reduce. Okay? Now let's think about sizes now. When we say the dimension of something is n, we talked about this before in the exam. When we say the dimension of the space is n, we said that's the largest possible linearly independent set and the smallest possible spanning set. So if you get a set of size n and it does one thing, it has to do the other, right? So using that relationship, I get the next couple. I told you we have a lot to add to our mega theorem today, right? The rows of A are linearly independent, and the columns of A span Rn. Because again, by size, it's a size argument, right? If the dimension is n, and you have a set of size n that spans, that's the smallest possible spanning set. It must also be linearly independent at the same time, and vice versa. Well, if something is linearly independent and it spans, what kind of a thing is it then? If a set of vectors is linearly independent and spans, what do we call that set? Basis. So that's the next two.
the rows of A form a basis for Rn. In the last one here, this will be the last one we add today. The rows of A, or excuse me, the columns of A form a basis for Rn. Like I said, there's a lot we added today, isn't there? This kind of summarizes a lot of the stuff that we've talked about over the last chapter. This is why there was a lot to add today. This is kind of a nice summary for you. Questions do you have? I told you we get to 20. What are we at now? 18? Yeah. Okay. We'll get more than 20, actually, it looks like, by the time we're done. It's very exciting. What questions do you have? All right. Well, let's go on to some new stuff, which is talking about dot products. Many of you may have already seen dot products. We're going to extend just like everything else in math, we're going to extend, abstract, whatever you want to call it, the idea of what we mean by a dot product. Probably the most important things about dot products is the idea of angle and the idea of projection. Okay? And we'll talk about both of why those ideas are important. Okay? There are other important ideas for dot product.
Maybe one more.
Did I not give you 4? What? I mean, I do have a problem. Like I say, counting's hard. Just ask anybody who does combinatorics. Counting's hard, but I usually get to 4 okay. All right. So let's talk about dot product. And first, we'll talk about motivation for dot product. So, in particular, I said one of the ideas that's important for considering what we mean by a dot product is the idea of angle. So, if I have two vectors in Rn, how do we find the angle between them? This one requires a little bit of trig. Okay? I know you're all very excited about it. We'll do it in 2 dimensions, but we'll see what's going on, all right? And then we'll extend this idea. Okay, so I know I'm going to have to remember some trig. So remember how we get to, I'll do it this way. If I add that third vector on there and make a triangle, remember that this vector, when I draw it in this fashion, this is v minus u, right? Yep. Okay. So let's call this point right here x1, y1, and let's call this point right here x2, y2. Okay. Then your vector v minus u will be x2 minus x1, y2 minus y1, right? Subtracting those two. Okay. So let's see if we remember some trig. Let me draw this off to the side, and then we'll come back to this. Okay. If I have, let's call it triangle ABC, and I have sides A, B, and C, I can relate the 3 sides and the angle through the law of cosines. Before we remember law of cosines, you should remember Pythagorean theorem. What is Pythagorean theorem? Yeah, the a squared plus b squared equals c squared, where the right angle is across from where the c is, right? Right? So this is if the angle between the side A and the side B is 90 degrees, right? That's Pythagorean theorem. So the law of cosines is just an extension of the Pythagorean theorem. It starts off exactly like the Pythagorean theorem does, right? Okay. Now think about what happens. We're not gonna prove the law of cosines because that's not the important part of this class. Take trig if you want to go prove it. Okay. Or come see me in the office. I'm happy to go through it too. Okay. Got a whole handout for it, everything. You can go through it piece by piece if you really want to. I bet you lots of you here are coming up and taking up on that offer. Okay. But let's think about what has to happen. If your angle goes from 90 degrees and becomes smaller, does your length of C get bigger or smaller? If your angle, that angle at C, so between A and B, if that goes from 90 and becomes less, does C get bigger or smaller? Smaller, right? So I should be subtracting something off if the angle is smaller than 90, right? What happens if my angle gets bigger than 90? Does C get bigger or smaller? It widens out, right? The wider the angle, the wider the, that just flashed there. Weird. The wider the angle, the longer the side's gonna be, right? So I should be adding something on. Now think about your cosine function. If your angle is between 0 and 90, cosine, is it positive or negative? Between 0 and 90? Positive. Between 90 and 180, it'll be negative. So again, remember, between 0 and 90, I want to subtract something off. Bigger than between 90 and 180, I want to add something on, right? So what goes on the end of this will be a subtraction. And I'm not going to tell you why the different number. That was weird. It'd be minus 2AB and then cosine of the angle between them. So again, if your angle between them is between 0 and 90, it'll be positive, so we'll subtract something off. If it's between 90 and 180, it'll be, pardon me, it'll be bigger, or so it'll be negative, and we'll add something on. Okay, does that make sense? All right, we're going to use this to help us talk about why we care about dot product, okay? You already know how to do dot product, but we're going to talk about where this formula comes from by doing law of cosines, okay? So here would be my angle between. So these are my adjacent sides, okay? So according to the law of cosines, and I'm going to use some notation here, and you've probably seen the notation, and we're going to use this notation as we go forward. The length of the opposite side squared. So the double bar stands for magnitude or length. So I'm just using that notation to talk about the length of that vector is equal to, oops, the sum of the squares of the other two lengths minus 2 times the lengths of the other two sides times the cosine of the angle. Now the idea here is that I want to solve for cosine of theta. And you've probably seen this formula in Calc 3, if you've had Calc 3. Probably seen the formula in physics, if you've had physics. Okay. Pops up in all those places. But let's just, and I'm not going to worry about figuring out these values. I'm going to concentrate on these. Okay? And play around with those. So this is length squared. Well, we can do length just by Pythagorean theorem, right? If I think about where this point is, you go right x1 and up y1. So the length of the hypotenuse will be x1 squared plus y1 squared. And do the same thing for the other vectors. Okay? So on the left-hand side, we'll have x2 minus x1 squared plus y2 minus y1 squared. On the right-hand side, we'll have x1 squared plus y1 squared plus x2 squared plus y2 squared. And I'm not going to do anything with the other twos. I'm going to leave them as their notation.
What's about if I spend like remember green option?
I'm sorry?
Putting the option.
That is the notation for length of a vector. This is the notation for that. That's the definition of the notation.
Cellophane.
I mean, this notation literally says go find the length of the vector and square it. In general, the length of x1, or call it xy, the length of xy is square root of x squared plus y squared. That's just Pythagorean theorem, right? Yeah. Okay. Now let's just multiply things out and see what we get. We FOIL out the left-hand side here. We get x2 squared minus 2x1 x2 plus x1 squared, don't we? You agree with that? And get the exact same thing in the second binomial that we square out, except that I'm changing the names to y's instead of x's. Okay? This is not bad algebra at all. Okay. Again, the whole motivation behind this is to solve for cosine, right? That was the whole motivation we said. If I solve for cosine, the first thing I need to do is subtract all of that over to the other side, don't I? What happens when you send all that to the other side? They all cancel, right? These things all here all go away, don't they? Now again, if I want to solve for cosine, I need to divide out that, don't I? Notice also when you divide out, your negative 2's will cancel, won't they? So when we actually solve for the cosine here, I can get that to get my black again. When I solve for the cosine, you'll get x1, x2 plus y1, y2 over magnitude of u, magnitude of v. Again, we know how to calculate these things because that says magnitude, right? That says length. We know that from Pythagorean theorem. Notice that we've got this nice, special thing up here, don't we? It's a special product of multiply your first components together, multiply your second components together, and add them. That's where the dot product definition comes from. So for these two vectors, in this case, when you've got your u equal to x1, y1, and your v equaling x2, y2, your definition of dot product for these two vectors will be x1, x2 plus y1, y2, which is your familiar formula for dot product, isn't it? But that's where it comes from. It comes from law of cosines. It comes from the motivation is how do I have a numeric way to help me talk about angle? In particular, you've probably talked about this in Calc 3 if you've had Calc 3. The important angle we care about is 90, typically. When are they perpendicular to each other, right? How do you check that with a dot product? The dot product is 0, right? Because cosine of 90 degrees is 0. Then you have two non-zero vectors. Their length will be non-zero. So the only way that this could equal 0 is if the dot product is 0, okay? So that's going to be a nice numeric check for us as well for when they are perpendicular. We're going to have a fancy word for it later because not all dot products are Euclidean dot products. Okay. Orthogonal is the fancy word for it. Yep. Okay. All right. So let's do it in general, though, for Euclidean. So we extend this from 2 dimensions to n dimensions. Your u dot v will be, I've got it written in u's and v's. Of course I do. u1 v1 plus u2 v2 plus un vn. That's the definition of inner product. I know we say dot product a lot, and I'll say dot product a lot as well, but the more abstract word is inner product. So what are some properties of these? And we'll talk about these. I want to make sure I put them in the same order as the book does while I'm opening up the book. We'll talk about some of these properties, and we'll do more of these on Friday as well. But some of our properties of our inner product are the following. Well, certainly from the definition, hopefully it's pretty straightforward to see that doesn't matter the order. Because what does the order getting switched around do? What is it? If I look up by definition up at the top of the screen, what does switching the order do? What does switching the V and the U do? It just flip-flops those things, doesn't it? All those are real numbers. Real number multiplication commutes. So I don't have any issues there, right? Okay. Another property, and this is would be just playing with the formulas. It's a product and a sum. What would you like that product to do relative to the sum? Distribute. And guess what? It does. Okay. Again, this is not too bad to prove, just using the definition of what the inner product is. Okay. It's just playing around with the symbols. Okay. The next one just talks about where the constant can go. The constant could go here, or it could go on the first one, or it could go on the second one. Oops. Okay. That's all the third one says. Again, for reals, for the Euclidean inner product, it's not hard to check these. You literally just use the formula that we came up with. The fourth one's a weird one. Okay. Notice that going back up to the definition, just for 2 here, if I do U dotted with itself, you would get x1 squared plus y1 squared, right? That ends up being the length of U squared, right? I get rid of the square root, right? What vector should be the only vector you come up with that has length 0? What should be the, well, for Euclidean it's pretty obvious. But in general, if you're talking about lengths of vectors, what vector should be the only one that has length 0? The 0 vector, right? So that's what the fourth property is basically telling us. It says that first, U dot U is always greater than or equal to 0. Okay. Because again, if we think about this in terms of length, if I square the length, I better get something that's always positive, right? And the only way a vector can dot itself to 0 is if that vector is the 0 vector. Okay. Again, this is specifically for lengths of vectors. The first condition, and it's not too hard to see why this is true for Euclidean vectors, right? Because when you dot a vector with itself, you'll square the first component, you'll square the second component, and all the way down, and you add them all together, right? That can't be negative, okay? And the only way it could possibly be 0 is if you do square 0 plus square 0 plus square 0 all the way across, right? Okay? So that's what this is saying. Lengths have to be positive, and the only vector that has length 0 is 0, okay? Hopefully it's fairly clear that that's true for Euclidean vectors, but again, remember our goal here is to extend this to other spaces. In particular, we want to be able to extend this notion to function spaces. Do functions have components? Can I write them as vector components? No. My functions look like e to the x, or x squared, or sine of x, right? Or cosine of 3x.
Those aren't components. If I want to extend this notion to spaces that aren't our Euclidean vectors, then I need to have notions of what I mean by length being non-negative and the only thing having length 0 is 0. Okay? That's important later. Okay. All right. We'll talk about more of this on Friday. I do have an assignment for you though. If you plan to do it, I have an assignment for you. Well, we'll talk more about these on Friday, as well as talking about extending these ideas to other types of inner products. Like I said, again, our entire goal, even though we might not do much with it this semester, our entire goal with this is to extend this and be able to do approximations of hard functions with functions that we know. Okay? That's kind of the whole point of doing all of this, by the way. So we'll talk more about that hopefully as we go through the next couple of weeks. But have a good one, and we will see you on Friday, if not before.